So what does that mean we're doing there, Chelsea? F of g of x.
You're plugging in for x for f, the g of x.
Yeah. So g of x is 3x. What does it look like when you plug it in?
2 over 1 plus 2 times 3x.
Nice. So when you square that quantity, Chelsea, what does it become?
9x squared.
Good. Don't forget, you're squaring the 3 and the x. Both of them are squared. So then we have really 1 plus, she said this is 9x squared. When we double that, we get 18x squared. Don't over cancel things. That's actually as far as you can take it. So don't be like, oh, well, 2 and 18, I'll just cross those off and make it 1 and 9. No, you can't do it to the 1. You can't do it to the 18. You have to do it to both pieces if you're canceling anything. So 2 over 1 plus 18x squared. The second one, this one says g of g, which if you wanted to rewrite it, you would write it g of x. So that would be the other form. So Nick, what are we doing here with g of x?
3 of 3x.
Nice, which is?
9x.
Yeah. So you're taking g of x, which is 3x, and you're plugging it back into x again in the g function. So 3x gets plugged into x, which is really 3 times 3x, which is 9x. Questions on that one? All right, so the last one's a little evil.
Why?
Because it has beautiful fractions in it.
I don't think fractions.
Yeah, that's why you would think it's evil.
You
So
like fractions, don't you?
I like them. Yes, I don't mind them. We have f of x, which is 2 over 1 plus 2x squared. But our goal is to find f of 4. So if we work ourselves from the inside and get that number and then try and apply it to the outside. The inside is just f of 4. So that's 2 over 1 plus 2, and then x is now 4. So right away, like you're plugging it into a fraction. On the top is 2. What number is on the bottom? Chelsea? 33. So it isn't even anything that like can reduce, because you got 2 over 33. That part is what f of 4 is equal to. So instead of having f of 4, we now have 2 over 33. And we need to take f of that answer, because we did f of 4, and we found a number. So now we need to do f of that value. So a second time, going back to that same function, 2 over 1 plus 2, but instead of x squared, we're now plugging in 2 over 33, which is just a lovely number to square. So we plug 4 in first, we got an answer. We're taking that answer, plugging it into f a second time. You might need a calculator to square 33. I will admit, I had to look it up in the calculator too. Didn't have that one memorized. So squaring the 2 becomes 4. What is 33 squared, Chelsea?
1089.
1089. So I'll probably have that number memorized for like the next 3 months, and then I'll forget about it again. Okay, so simplifying on the bottom, we have 1 plus, this is really 2 over 1 times 4 over 1089, which is 8 over 1089. And when you add 1 to that, does anybody know what that makes when you add 1 to it? Libby?
1097 over 1089.
Yes, so 1097 over 1089. Because if you have 1 and you have a common denominator, you're really adding 1089 over 1089.
I'm going to assume that 1097 is prime.
Yeah, of course it is. Yeah. All right, one last thing. So there's a 2 on the top here. That's the numerator. All of this is the denominator. When you divide by a fraction, Libby, really you are?
You are doing 2 times the reciprocal of the
Excellent. So you're taking 2 times its reciprocal. So 1089 on the top, 1097 on the bottom, gives us a beautiful answer when you multiply it by 2 of 21, is it 78? And that's your final wonderful fractional answer there.
And you can't even.
Nope. Emerson wanted to convert that to a decimal. The whole way
It's
through.
actually- It looks like a really big number, it's just like 1.9.
Yeah, it's not, yeah, it looks like it should be huge, but because these guys are pretty close to each other, it's almost 2.
It's like really.
So those are the fun problems, like to kind of work through. A little bit of fractions. Questions with composite or combination functions. Did anybody get that answer for number 3 or C? Ooh, a couple of you. Awesome. Good, good. Yay. And you had a calculator to help you. It's not like I said don't use a calculator. So today we're going to look at inverse functions. We needed to do the composite function because that's actually part of an inverse function, part of like showing that a function like is an inverse. So in your notes, if you look at section 1.6, 1.6 is divided up into 2 parts. So today we're just going to talk about the inverse part. On Monday, we're going to kind of combine the inverse part and the composite part and do like inverses of composite functions. So that'll be fun. A lot of algebra on Monday.
What will you when you think
Gonna make sure I sneak that back into your book bag.
no.
So, a little bit of like refresher about inverses and what an inverse function is. So if you think multiplication, immediately multiplication goes with division. And if you have addition, it goes with. And if you have x squared, it goes with square root. Oh, good. Good. Okay, so all of those are like inverse of each other. And the reason they're inverse is they're kind of like opposites. So to find an inverse function, what do? What do we switch? Chelsea? X and y. Yeah, so if you're dealing with functions, functions have an x, they have a y. If we want the inverse, we have to flip-flop them. So they're found by switching literally the x and y terms. So a little reminder, I'm going to show you a basic function of just a set of points. Just as a small refresher here. So if we have 1, 3, negative 5, 2, 6, 4. So that's our function. Find the inverse. When you have the inverse, we use that little negative 1 notation. It doesn't say I'm taking f to the negative 1. When it's connected with the f, that's the inverse function. So I'm not going to make that 1 over f or anything like that. That just means we have its inverse. What would the inverse of those 3 ordered pairs be? Which passes the vertical line test, so a function. So what's that inverse? Brandon?
3, 1, 2, negative 5, 4, 6.
Yep. So literally, you're just flip-flopping x and y in the ordered pair. You're not making something negative. It stays the same sign. X and y just switch. Now we have the inverse. And that's it. Like, inverse is really straightforward. Switch x and y. Underneath, it says to notice the domain of f. Remember, domain is the x. So if you look at the x values, 1, negative 5, and 6, they become the range of the inverse. Because we switched x and y, domain is x. If x was the range or the domain in the first, when you switch it, it now becomes the y or the range of the second. And that's the same thing with the range of the function. It's now the domain of the inverse. That's the same thing as saying, hey, we're switching x and y. So it was x, it becomes y. It was the domain, it becomes the range. So you might see both terms being used. We could switch domain and range, we could switch x and y because they mean exactly the same thing. So that was just a little basic intro there to inverses. In the little box, So it talks about the definition. Finding an inverse and defining an inverse are a little different. So that's how you find it, by switching x and y. But the actual definition, big stars around this. Remind yourself to look at it. Hint, hint, hint. Awesome. Two functions are inverses if f of g of x is equal to x, and g of f of x is equal to x. So they're not inverses just because I flip-flop x and flip-flop x and y. They're inverses because if I show that the composite can be x both ways, then they're inverses. It's like a little proof, it's a little verification. Underneath it says the same exact thing except with inverse notation. I can't speak. So the function and its inverse, if you do the composite of those, it has to be equal to x, and the other way around. So this is a conditional if and only if statement from geometry. The inverse and its function must also be equal to x. So we're going to try and show that with the next problem. We're going to show it algebraically and then see what happens with it graphically. So underneath, verify the two functions are inverses algebraically. Let's start with that. So if we're verifying they're algebraically inverses, we're going to show that f of g of x is equal to x, and we're going to show that g of f of x is equal to x. No, you're not going to like switch x and y and find a new equation. We have the equation. We want to verify, show, prove, whichever word you like best, probably not prove, that they are inverses of each other. So just like you did yesterday, just like we did the warm-up, take your g of x, replace it in the f function for x. So g of x is 3 minus x over 4. We're going to plug that into x. So instead of x, we have 3 minus x over 4. Instead of distributing the 4 through, what else could you do with the 4? Yeah, you can eliminate it, because if you're multiplying by 4 and dividing by 4, you just said they were inverses. They cancel each other out. So forget about multiplying and distributing it through. If you're dividing it, get rid of it. We still have a minus sign, so don't forget that minus sign gets distributed through the parentheses. So 3 minus 3 now plus x, because it got distributed through, is equal to x. So we've got one piece done. The 3's canceled. We've shown that that's equal to x. Now there are times where 1 will equal x, but the opposite way will not. So you do need to show both. So looking the opposite way, we're taking the 3 minus 4x, plugging it in for x in the g function. Don't forget parentheses when there's a minus sign. So distribute the negative through, do some canceling. 3 minus 3 is 0. 4x divided by 4, the 4's cancel. And again, we're left with x. So if they both equal x, they're inverses. If one is x and the other one is 2x, they're not inverses. Questions? So that's the algebraic verification. You don't want to say algebraic proof that they're inverses of each other. So now I want you to look at it graphically. So you have your calculator out. If you can put those two equations in your calculator. One in y1, the second one in y2. If you don't have your calculator out, that's okay too. Find mine somewhere. There we go. So when you put the second equation in, remember parentheses around the numerator if there's a quantity there. So 3 minus x gets parentheses. And then hit graph. All right, so this one's a little trickier. Because I think the next question, after we graph it, underneath it, you can kind of still see it on my screen down below. What is special graphically about these two functions? That they are inverses. So just looking at the graphs, there's something special about them. It's kind of hard to see. They do intersect, Virginia. Yeah, so kind of looking at those two sides after they intersect, they're kind of symmetrical. They're kind of like flips of each other. I'm going to type in a third line. And that third line is y equals x. If you type in that third line, like it's kind of hard to see, but this line, because of the diagonal y equals x, it literally flipped, reflected, but that's how it becomes. It's like a reflection. So that's how you get that second line. So we call it a reflection over y equals x. So you can have a reflection over the y-axis. You can have a reflection over the origin, where it like comes here and here. Or you can have a reflection over the x-axis. But this one actually reflects over that diagonal line. Which, in this case, like some of them are easy to see, some of them are a little harder to see. But that's what's special about the graphs. So that last little statement underneath says, what is special graphically about two functions that are inverses? They're reflections over the line y equals x. That's why they equal x. Like when we break them down and simplify them, they break down to become x because they're reflecting over y equals x. So like the two go together. It's not like coincidence. You have one because of the other and vice versa. Questions? So I'm going to show you a better graph of that. We're going to skip the bottom example, but if you flip it over on the top of the next page, so skipping the bottom, looking to the top of the next page. So the graph of an inverse function, if AB lies on the graph of f of x, then BA has to lie on the graph of the inverse. And we said just flip-flopping x and y, flip-flopping AB or B to BA. So I'm going to pick three random points here. We'll go with -2, -3. 0, 2, maybe? And how about 3, 4? So this is going to be some kind of random function that will connect kind of with like it's like a little arc there. They're not straight. One bumps out a little bit more. Oops. So what would the inverse function be? Brendan?
-3, -2, 2, 0, 4, 3.
And 4, 3. Okay, so that's our inverse function. So plotting these points. So when you connect them, it has to arch slightly the other way. I think it looks like a fish almost. But you can see the reflection a little better. So here's that line y equals x. I'll put that line in there. Y equals x is right here. So they're like flipping over, reflecting a mirror image over that line. Every graph that is an inverse to functions graphically will look like that. So they'll reflect over y equals x. Questions with that? So there's one final thing to kind of talk about with inverses. And that's the next little thing where it says the existence of an inverse. Not every function has an inverse. In order for a function to have an inverse, it has to pass the horizontal line test, which is pretty much the same as a vertical line test. Vertical lines test for functions. Horizontal lines test to see if it has an inverse. So if you say, yes, it's a function, then you can say, okay, does it have an inverse by testing it horizontally. This means that the function is a one-to-one, and I have tests for one-to-oneness graphically. For each x, there is exactly one y, so that's the function part, and for each y, there is exactly one x. So now you're looking left and right. So instead of one x having one y, we're flipping that. Does that y have one x?
So
That's-
parabola would not have an inverse.
Exactly. So parabola would not have an inverse. So it's called one-to-oneness. No, it's not like made up. If it's not one-to-one, we call it many-to-one. So, because it has many values. So Brandon said, he gave away number C here, letter C, not number C. So Brandon said a parabola would not have an inverse. If you draw yourself a little parabola, doesn't have to be perfect, just a little sketch. Here's our parabola. Your y value has two x's. So we would say this is many to one. Instead of one y having one x, now it's one y has two x's. This would not have an inverse. And I'll show you just so you can see the inverse, if it did have one, would look like this. Why isn't that an inverse? Brandon?
Because it still doesn't pass the vertical line test.
Well, this one doesn't pass the vertical line test. So it looks like it could have an inverse, but it's not a function. It still has to be a function. That's why we say that it doesn't have an inverse. Just looking at letter A. Letter A is x cubed plus 1. Remember, that's like the parabola that was like, I don't want to be a parabola. My right's going to go up, but my left side's going to go down. This one is one-to-one. Bless you. So this is one-to-one. Then it would have an inverse. So I had like 3 minutes, and I want to do one quick problem with you just to refresh how to actually find an inverse. So yeah, flip the page. I think there are 2 problems on there. I think one will suffice. You'll be good with getting one. Just kind of refresher here. To find an inverse, if it exists, and the book will say, check to make sure it exists first, check graphically. Plug it in your calculator to check graphically. First step, replace f of x with y. Okay, so now it says y equals. Second step, switch x and y. Literally, x equals y cubed plus 1. Third step, solve for y. So I have to subtract the 1 to the other side. We got to get rid of that power of 3, which means the opposite is the cube root. If it was y squared, you would take the square root. And then write it in f negative 1 form to show you found the inverse. So f negative 1 of x equals the cube root of x minus 1. We won't worry about sketching the graphs. You can plug it in your calculator to see that they're inverses. But like we started with x cubed, we have the cube root. We started with plus 1, we have a minus 1. So they look like they're inverses of each other as well. I know I only went through one of those and that was really quick. Questions? Sorry, I squeezed that last one in. So finding the inverse, literally switch x and y, get y by itself. Your homework is in the book, but then there's one page in the packet. I think it's page 35. There's 2 word problems on there. And I want you to do those 2 word problems. So just 2 word problems, fairly certain it's page 35. Questions? Anyone interested in doing one of those 2 word problems? Virginia?
Can I do both?
Both? Yes, that would be awesome.